everyone. So I'm Aida and this is Julian, just so that you don't
Hi.
confuse us. So just a bit about me. I'm a retired architect, retired BIM manager, retired computational designer, and now I'm leading the building analytics team at Herzog de Meuron. We do basically sustainability performance analysis for the projects. And Julian?
I'm Julian, and I'm a BIM manager, also retired computational designer, but looking also into the in-house developments, which we call the initiative we call Toolbox, and I'm kind of managing that one as well.
So, and today we're just gonna show you a bit of how we have been trying to implement Speckle in our strategy for for the projects, using it sort of as a common ground to enhance the way that we use the design data within the office. So it's going to be a quick introduction about the office, then what our main challenge is. Then we're going to show a couple of case studies, what the current situation is with Speckle and the development that we are going to talk about, and then what our next steps are going to be like. So Herzog de Meuron is a very international office. We are based in Basel, and we have around 550 employees all over the world, 35 different nationalities, so very international, 8 office locations. And our projects range from kind of big highlights, the big important projects like the Tate Modern or Philharmonie in Hamburg, but we also do a lot of local projects in Switzerland. So we have this ski lift station. It's called Kesserog. It's in the Alps, and we also have some other kind of big impact projects that are coming. So like UCSF in San Francisco, just to give you an idea of what type of projects we do. And we are part of the design technologies team. So the design technologies team is within Herzog de Meuron, sort of looking at the intersection between the design and technology. So we focus a lot on the process of all the projects. So we go from sketch to the final product, like everything that happens behind the scenes, like how is the process working. We are kind of involved in that. And we are divided as a group in 5 different domains. So we do project delivery, which is BIM, computational design, typical computational design scope. Then we have the visual artist. Building analytics is the latest addition, which takes care of sustainability and performance analysis. And then we have workshop, which is both a physical workshop and digital workshop. And we all work together as a sort of, even if we have different groups, we work as a collaborative kind of group on different initiatives. So there's always a bit of involvement from a person from the different fields in different initiatives. And what we are mainly going to look at today is our challenge that we have as a group, sort of with data. And this comes, this is like a global problem within the office. And this comes basically from the fact that the type of projects that we have are very varied. So we don't have one specific scale or one specific typology that we are kind of bound to. We range from kind of the design of little objects to master plans. And in terms of typologies, we do a little bit of everything. And when you work in an international setting, of course, what happens is that you cannot really define a standard for any of these projects. Also because of the type of design that we do, we are very experimental in terms of solutions, materials, facades, etc. So it ends up being sort of everyone wants the same, but it's always a bit different. So the same, but not. So also when you think about BIM standards and with different clients, you end up with this kind of problem. Then another issue that we have is that when you think about the design phases that we are involved in, it's sort of, it should be a very linear process and it should be very easy, one phase behind the other. But in reality, the way that we work and at the speed that we work, it ends up being very chaotic. So you have a lot of different design options. You need to do analysis and simulations at one point. You have a BIM model that is going through 2 different phases at the same time. So it's really kind of a chaos in terms of how the reality works. And then when you think about the data production throughout this process is just like, it gets kind of like, it grows exponentially. So at the beginning, you maybe start with just a couple of models, but then by the end of the project, you already have kind of like a mess of all this data that you have produced. And the question is like, how do we manage this with the tool ecosystem that we actually have in the office? So we produce this data with many different add-ins, softwares, and in the end, where is this data living, and how can we kind of like take it and compare it if it's actually not standardized at all? So we started looking at the way that the design data process works in the office right now. So it's like very typical. You have like a folder where you put all the kind of like start files, and then you start the process of your design. Then at some point you start producing a lot of data during this design with either iterations or like analysis of this, analysis of that. And then at the end of the phase, you kind of like pack it all up and put it in a folder. And then you end up with this kind of like single files that are really just saved in this folder structure. And then you kind of like cannot do anything with it. And for us, that's completely a dead end, because throughout the entire process, you lose some of the data. You don't really know where it comes from. You have a lack of transparency on how this data kind of like was produced. Sometimes there's inconsistent data, you cannot compare it, and there's always the software versioning problem that you want to look at what happened in a file that is Rev 2021 and no one has that version installed anymore in their computer, so it's always sort of like a struggle. So basing ourselves on this, we sort of understood the challenge as something that we want to sort of understand how could we efficiently store the project data throughout the design process, but it's also like meaningful data, not just like saving thousands of versions throughout the process, because that's also not relevant. And how do we make this data transparent so that we can assure the quality control of the things that we are seeing in the end? And what standards do we need to create, and kind of like which best practices we need to apply throughout the entire office so that we can make this data comparable between the different projects? And in the end, what we want to achieve is sort of like a sustainable process that allows us to have flexibility with this data that is not just like living in one specific software or in one specific format. So what we came up with is, we call it the improved design data process, which is that we look at just the basics of how it works, and then we try to kind of like add another layer within the design phase, where we can say we're going to monitor key aspects of the project that are relevant for us to compare at the end of the process. We're going to look at project milestones, so these key aspects throughout the project milestones, and then we, at the end, are going to be able to compare projects and then get some insights into the projects itself, so that there's always this question within the design teams, how did you guys do it in that project? And then we sort of explain how we did it, but there is really no way for them to look into it. And this is something that we sort of wanted to also give the people to kind of like give information, extra levels of information. Then what we had already sort of like a bit of a strategy of, we are using a centralized database, so Directus, where we were saving already some data, but when we noticed that we needed to also kind of like add another layer to it, and that's when Speckle came into the picture. So with Speckle, we basically are saving the geometry data, so like the beam data, so let's just call it the raw model data, so like unmodified data that comes from the project. And then Directus, it's a bit more kind of like our centralized database, where we save information related to the project settings, also kind of like some processed model data or externally sourced data, like, I don't know, material libraries and other types of things. So we try to create a system that it's not kind of like duplicating this data, because of course this is also not efficient, and they sort of like kind of like support each other in a way. So our data pipeline looks a little bit like this. So from the design team side, they are in charge of creating all the data. And then we, as design technologies, come in as kind of like the middleman that is in charge of creating like different apps or different workflows or systems that kind of like extract, transform, and load this data. We call that a project snapshot, so it's sort of like a standardized method of saving the information from the project. And this is saved within our repositories. Then we are in charge also of sort of like filtering these milestones again, and then create the analysis and sort of like distribution system that it's again now embedded into what we call the project platform or knowledge platforms within the office, where the teams can actually access the data of the project and sort of like inform back the process. So this is for us like closing the entire loop of the design data process creation. And just to give you an idea of what these key aspects are, so we are looking at different things, like these are case studies, let's say, that we are developing. We started with areas, which is something like very straightforward, but still like quite complicated to compare between projects, especially in different settings. Then we also looked at embodied carbon, and that's what, and operational energy will come later, but this is sort of just to give you an idea. And then our vision is that when you have a project, you have like all these different moments throughout the project that are not specifically milestones, but you have iterations, and then you have all these key aspects that you are tracking, and then you sort of like create this snapshot that lives within our repositories, and then from the project's platform, you just grab the information that you need, which is relevant for the project to compare the different projects. And today we're going to talk about the area schemes and the embodied carbon case studies, and Julian is going to start with the areas.
Yes. Our first case study is talking about the areas, and the area in an architectural project is a very basic metric to evaluate the project, the area, the GFA, as well as the room data. And also this case study is a bit introducing this snapshot milestone concept that Aida was already showing. Just quickly to see where the project area is appearing in a project. It's not only the project itself, but it's also the metrics that you could evaluate a project for that contain always the square meter. So you actually, to calculate any metric, you might need the area to be able to get good results. As we have a lot of projects all over the world, we have a kind of a challenge that in different regions, there's different requirements, there's different standards for area calculations, and there's also the clients that might have very specific requirements on the models. So it differs from our office standard that we, of course, also have. That means that our end results, as we've seen also before, here, 3 projects result in 3 different PDFs that have different values, maybe by a different regional standard, and this ends up in a dead end for us, where we are not able to actually compare or go back in time and see how did the project develop, but we only have multiple PDFs that we can look at. This is another representation of these 3 projects. No, we have different standards. The geometry, of course, differs over time, also between different projects and the data. But what we want to kind of harmonize and kind of use to have these elements comparable is the standard itself. So this is kind of what we in our office decided to do with the SIA 416, which is a simple and straightforward area standard from the Swiss Society of Engineers and Architects. It's the gross floor area divided into sub-categories: main usable area, circulation area, technical services, and construction area. This is due to the fact that we have 50% of our projects in Switzerland, and if we might need to standardize other projects, we go for this method. But there's another more important challenge here, where we also use our Directors and Speckle methodologies, is the value comparability. You have different clients, you have different parameters that classify the areas, and over time you have maybe an upgrade of a Revit version within one project or different Revit versions between projects, and this is what requires a possibility to kind of harmonize these elements. And what we need for this, besides Speckle and Directors that we've seen before, is a little app that we created, which is the Area Bridge, which is a streamlined model versioning with automated area calculations and data organization. So this is basically there to kind of put the two sides together. But we'll look into that in the next slide, where we see how this process is going to happen. So looking back at the project with its different iterations, over time you have the possibility with our Speckle connectors to send the data for each iteration or even studies to the Speckle model. So your result is a Speckle model with n versions. This is the serialization, so we have the possibility to compare the models no matter from which Revit version they come from. The next step, which includes the area bridge, is how do you kind of harmonize this data, meaning that there's a project setup that basically knows which parameter holds the area classification of this specific model. In the area bridge, there's also the receival happening of the model versions from Speckle. It calculates the results based on the setup, and you are able as a user to link that specific version to a specific milestone. For example, a schematic design milestone, where you then can actually save. By doing this, you can save this snapshot that actually holds the data of the specific milestone information, the version from Speckle, and the results of the data, area calculation. So we end up with a collection, an organized collection as database objects that hold these informations of the area calculations, which makes it very easy to basically independently being able to compare different snapshots, but also keep the connection to the actual Speckle model. Of course, we want to also see that live in a little presentation here. So we have the Revit model. We use the standard Speckle connector, which is connected to setup project. We send only the room data in this case. Then we have to utilize the Area Bridge app, which is a web app that we start here from Revit directly. Here you choose the area configuration. This the project configuration knows its Speckle project and model, and it knows the parameters that it has to evaluate. And you see the versions in Speckle that you can query here. And basically by selecting one version, it automatically calculates, or it can calculate the area values, and then you can save this as a new milestone. So in this case, we save the latest commit as the field engineering milestone. So we have now a DD milestone that relates to a certain model, and here the FE milestone that knows its Speckle model that relates to it. What is the result of this? The result is a very clear, organized database where you have a relation to the project. You have the milestone that you defined as a user that relates to the Speckle version ID and the URL, as well as the calculated area for each of those snapshots. This makes this data comparable. We have basic area data for all metrics. We have a complete kind of set of data because it's organized by milestones, so we can go back and forth in time per project. We're flexible because we have always the geometry and the milestones that we can reassign also, and it's updatable via this area app. And it's transparent because it's verifiable, because we can go back to the Speckle model and check if what is actually the geometry where we got the results from.
Yes. And so now I'm just going to talk quickly about the second case study, which is CALC. It's our embodied carbon calculation tool that we developed in-house. So what is CALC? It's basically just, as I said, to calculate the carbon emissions of our buildings. So it's a very simple kind of like method of calculation. We are focusing on the embodied carbon, so like the beginning of the phases. This was never meant to be sort of like a tool that replaces any of the existing tools in the market. You will see how kind of like our approach and the way our thinking was. So basically, we define different levels of an LCA calculation depending on what information is available like at that moment of time in the project. So we have like from very schematic to kind of like very, very detailed calculations that are dependent on specific EPDs or data. And what we saw is that at the beginning of the process, because of all the design iterations that we do, we don't really have, first of all, enough time, and second of all, enough information within the project, because our solutions are never sort of like standard solutions when it comes to design, to kind of like figure out what the actual embodied carbon of this box was going to be. So we decided to take sort of like a costing approach, where we try to make an estimation based on kind of like references that are already kind of like built and already exist. So we are kind of like going in reverse. So we decided to focus on like very detailed elements that are already kind of like calculated with specific data, that it's reliable, and then we just use that at the beginning of the project to kind of like have some benchmarks and reference values to kind of like guide us and understand how much embodied carbon or how much budget we have for our project. So then this became kind of like an idea to develop this assembly library that it's formed from, like, it has different levels of detail. So we are basing ourselves on these assembly elements that we do the calculation for. There are very detailed like elements, and then you get like a price per square meter or per unit of that element. And then when we combine those, we call them assemblies. Elements, and then the next step would be to put them together and then create what we call the assembly systems. And in that case, you could do kind of like an even more you could have like a less detailed model even, and maybe to try to figure out how much carbon you would have based on that. These elements in general, they're not just meant to be geometrical and have just one number of embodied carbon attached to them. They are meant to have more information, because if we want to make this information available for the architects, we need to make it comparable. We need them to understand, can I use this in my project, just so that there's no kind of like slab system that is being used in a laboratory building that cannot resist the loads of that specific project. No? So we decided that we needed to attach a lot of information to these elements, and also keep that at the end of the calculation, so that you can always go back and see, okay, what was this calculation made with, and it's not just a number at the end of the process. So then the way that this works is that you can have assembly systems, and then you can apply them to very simple volumes. And then you get like a quite detailed calculation, because these systems have elements in them. Or you can also have the option of having a more detailed model, and then you kind of like assign these assembly elements that are a bit more individual to this model, and then you get in the end at the same type of detailed calculation that could guide you and say, you're going to have this much amount of carbon in this area of the building or in that area of the building. And the way that we did that is with our tool CALC. It's working within Revit at the moment, but it is meant to be also used in the future, maybe in Rhino. So we have two modules. The first module is the CALC builder. The second module is the CALC project. With one, you create these assemblies, and with the other one, you sort of like apply these assemblies to your Revit model. The way that it works is fairly simple. So you have to draw in Revit, for now, the specific elements that you are going to calculate. Then with CALC, you grab the material data from, we are connected to Materials 2050 API, and then we have there stored the data in Directus. And then you kind of like have this connection between the Revit elements and the material data within the Revit software with CALC Builder. And then you end up with an assembly that gets sort of saved in Speckle and in Directus. So the same way that the areas communicate, and what Julian was explaining is the same way that it works here. And then this data you grab again from the construction catalog that sort of like shows you all the assemblies that are available that we have already kind of like worked in the office. And then when you go to the next step, this would be the part of the projects. So you have your model, and then you can access this assembly library and kind of like apply it to different elements. And then from CALC project, you grab again configurations for your specific project from Directus. And in the end, what you get is this snapshot that again gets saved in Speckle, Directus, and then you grab that information from the projects platform. So in the end, what it ends up looking like is that we have two assembly repositories. So one in Directus that has mainly everything that has to do with the calculation of the embodied carbon, and this is because we have relations between the results of the elements and the actual material databases that we also store within Directus. But then at the same time, we are sort of like attaching the information of where this element lives in Speckle, because everything that has to do with the performance or the geometry itself is sent to Speckle. So it is important to have that relationship, but we also don't want to have duplicated data. Then when it comes to the project snapshots, is the same logic. So you create a snapshot, you send the model to Speckle, where you can see actually only the information that was part of the calculation. So if there was something that was not included, it does not get sent, so that you can have a reliable source of what information was in there. You do the different snapshots, and in each snapshot, it's sort of like it gives you a file with very raw results that include everything that was included in the calculation, included the kind of these assemblies that we were talking about. And just to give you a very quick kind of like preview, it's a bit fast, but it's just so that you kind of like understand how this calc environment looks like. So you can create the assemblies. In this case, it was already saved, but you kind of like tap into all the materials that are part of that element, and then you can apply one or multiple materials to it with different ratios also. You save the performance information that is saved as parameters in the elements. And then once you upload it, then this element would be available for the project team to kind of like do a calculation. We have a way of filtering and grouping the model that it's already, these are the project settings that get grabbed from Directus. And then in the end, you can sort of like have a very detailed model that will kind of like map specific elements, or you could have just a box and then kind of also just take either areas, volumes, count of elements, or the length of the element, depending on the unit assigned on the assembly. So this entire kind of like process started kind of also like another different thing that we wanted to kind of like make available for the office, which is sort of our knowledge, like this web-based, it's also based in Power BI, so like an assembly library that the teams can look for, and kind of like where they can compare elements and they can see everything that it's included in that element, how they compare to each other, in which project was it used, what program was it, and basically give the teams full transparency on what is being done. And this we saw something that was very necessary for us, because the LCA calculations were being done mainly by ourselves, by our team. And we kept seeing like PDFs of like the repeating calculation from all the references that the teams would take from another project. And there was just so many things that were wrong. The calculation was including something. So we just kind of like decided that this is the approach that the office needs to take from now on, sort of like centralized, transparent, and kind of like shareable. So then in the end, our goal was no more PDFs, so centralized, accessible, and updated, and you can update it easily. It should be comparable so that it makes benchmarking possible, and then it should just be flexible so that it can be transferred to multiple sources, so it doesn't just live within this dashboard. It can also be grabbed back into Revit, or it can be grabbed back into Rhino, and the team can sort of like start making variations of that. And then when it's a final product, we send it back to the library, and then it's sort of living there as a knowledge sharing. And then it's transparent. You can see everything that is part of the calculation, and then you can track the process all the way until the beginning. Now Julian again for the ending.
Last part, how do we look at this, these snapshots that we saved as data in the office, like a user-facing interface? That we think of is the projects platform. So we consolidate the project-related data and the metrics we were just talking about. Of course, the visual content of all these projects that we were realizing is already there, and we have an archive for that, but it's not connected to the data yet. And the idea is to kind of put this in this project catalog or this project platform, where we have a user-friendly entry point to allow the user to choose projects by various parameters, which is project status, current phase, or BIM level, before they go into maybe a detailed look at specific metrics. And this should make also the data and kind of snapshots that we saved transparent for the user, because the database is not very kind of visible for the user. But here, in combination with the Speckle model, for example, we can very clearly see where is the global warming potential, what are the numbers. They are also related to the calculated area from this area use case study that we've shown before, which would look maybe on the next page like this, where you, of course, have a Speckle connector also for specific project analysis, but especially also having the possibility to compare different projects and different milestones of a project, maybe not only the overall area, but also the efficiencies of different projects. Of course, always related or linked to the actual Speckle model from where the data comes from. Just quickly an overview how we want to organize these two kind of parts. And we have on the top, we have the Speckle project repository, where we kind of divide things in different folders for area scheme models, project setup models, design versions, LCA calculations, and GIS assets. And on the other side, in directors, we have the related snapshots, or just kind of like data tables that contain certain information, but they are always related to their Speckle model and know the ID and the current version of the Speckle model, so that we keep kind of the connection between these two platforms. So this is kind of our back end, let's say. And then quickly about our next steps, we want to finalize and publish the project platform by adding content of all running projects. We want to use the assemblies that Aida showed not only for the calculation of the LCA values, but also as assets for Rhino and Revit modeling. We want to develop the use case for the operational energy of projects to include that in the project platform, improve the GIS asset library, and use potentially like Speckle Automate to make some of those processes even more efficient.
Yes.
A bit over time, but that's it from our side.
Thank you.
Thank you very much.
Okay, thank you, Aida and Julian. I am Mirna. Do we have any questions? I think we're okay with that. Oh, no, there's one for you.
Thank you very much. Axel Alvarez. Thank you very much for the presentation, like, amazing. Thinking about Herzog de Meuron, so, I mean, when I was in the university, I was thinking, so Herzog de Meuron, poetics of the materials and that kind of stuff. How does this work inform, like, the design culture inside of the company?
So we are, I mean, within the office, we do have that part, right? So it's like materiality and kind of like looking at the project. It's like kind of like a philosophical almost way, right? But in the end, we also we look at a lot at previous projects as reference for ourselves. So this is something that we do a lot. So you kind of like take inspiration on things that have been done before. And kind of like try to see if there's a solution there that could also kind of like help you solve the problem that you have in this specific project. And this is something that I think it's part of the way that the office also works, right? So it has been always kind of like an internal process, and it's also very kind of like difficult to find this information. I mean, we do have an archive of everything that we have ever produced, so it's like it's really kind of like a department in itself, and what we are trying to do is kind of like make this information more available when we want to look into these insights of the other projects, because the questions always come up. Everyone is just always asking the same thing: which other projects had this problem and how did they solve it? And this is something that it's always a bit difficult to figure out if you don't have the data available and kind of like shareable for everyone.
Especially because the LCA data is getting more and more important now, and as you said, with maybe also custom-made materials, we want to know and document to be able to actually compare these materials to each other. I think this makes it possible.
And there's a big culture of knowledge sharing in the office. So we do create kind of like process documents of everything that went through the process in like a specific project or in specific or in facades or things like this. So this is just fitting into that, but it's not just digitalized.